8M3 lesson 13, proof of the Pythagorean theorem. Now you say, well, didn't we already do this, Mr. Lipscomb, in 8M2 lesson 15a? Didn't we already prove the Pythagorean theorem? Well, yes, we did, but it turns out there's another way you can prove it using similar triangles. And so we're going to do that today. It might take 20, 25 minutes to do that. At the end, I'm going to give you one homework help problem. The homework is a lot easier than the proof. So we'll just take 5 minutes to do that at the end. It's so if you don't need the proof, I encourage you to just watch it, listen to it, see if it kind of makes sense. I don't expect you to do it from scratch. It's involved, but if you should be able to follow all the steps because we've had all the building blocks. So just bear with me, watch it. You may have to know how to do some of this for your test. Your teacher may expect you to know how to do it, and maybe you have to memorize it and reproduce it. So again, let's get going. And if you don't need the proof, just fast forward all the way to the homework help, and we're going to do one homework problem, and then we will be done with today. So let's get going with the proof, and here we go. All right, so we're going to start off with a triangle, a right triangle, A, B, C, and it's a right angle. A right triangle, because the Pythagorean theorem, and so let's label the sides, and we're just going to label the sides. Opposite A will be side A, opposite B, angle B will be side B, and this will be side C, right? And the Pythagorean theorem, we've already learned, says that A squared, where that's the length of that side, plus B squared equals C squared. That's what it says, and we're going to prove that this is not only sometimes true, but always true. Now, again, we've proved this back also in 8M2, lesson 15a, and this was another proof, an alternate proof of the Pythag. Will this be cool? Called the Pythag theorem. Okay, want to go back and look at that one? You can. We did it back then. Okay, but this one's going to do it using similar triangles. Now, the interesting thing, so we're going to do this in 3 steps. 3 steps. The first step, I'm going to prove to you, we're going to build 2 subtriangles, and show they are similar and similar to big triangle. That's step A. Step B says we're going to build some relationships, between sides using our knowledge of similarity. Don't worry about writing this down. I'm just breaking it down for you. And then C, we're going to do some algebra using B, what we did in B, and showing Pythag theorem. Okay, so that's what we're going to do. This is how we're going to do. This is our strategy. Let's see. Let's see here. Strategy. Okay, whatever. This is our strategy. Our 3-step strategy. Okay, so the first thing you can do is you can always, whenever you have a right triangle, this is the key. This is one of the key foundations. You can always, when you have a right triangle, you can drop a line, and I've actually marked the magic spot from the right angle, the vertex that is the right angle, all the way to the hypotenuse. You can always drop a line like that that creates a right angle. This is key. Right? So this is now a right angle. And that makes this also a right angle. Right? These are right angles, and I'm going to label this point D. Okay? Now the key. So we've built two subtriangles. So we have triangle BDC from here to here to here. We have triangle CDA, CDA, and then we have triangle BCA. So these are our triangles. And I kind of went from using the big angle to the right angle to the small angle, and you'll see why I did that. So the big angle to the right angle to the small angle, that's this triangle here. Now let's do this one here with the big angle to the right angle to the small angle, right? The big angle to the right angle to the small angle. So that would be CDA. And then we're going to do that for the big triangle, BCA. So this is, we're going to start with the big angle, B, the bigger angle out of B and A, to the right angle, BCA. Okay? Now, the interesting thing about these triangles, and I kind of gave you the hint over here, and said that they're similar triangles. Now, how do we know that these are similar triangles? There are some proofs that you'll see. I think the video that is linked to in this lesson shows you that it just kind of makes the claim that they're similar, and it kind of helps you a little bit on the way, but I want to really prove this to you. So let's just take, first of all, let's just look at this triangle, BDC. We're going to look at this triangle, and we're going to look at the big triangle. Let's not even look at those angles. Let's look at, I want to show you that angle B is the same as angle DCA. I want to show you that these two angles are equivalent. Okay? So let's try that out. So if those two angles are equivalent, then I want to show you how I know that's true. Okay, so let's look at angle B, at triangle BDC. And so we know that angle B plus angle BCD. We know that this angle plus this right angle equals 180 degrees. Because all triangles equal 180 degrees if you take the measure of these angles. Now, we could just say also that these two angles added together equals 90. So let's do that. Measure of angle B plus measure of angle BCD equals 90. Because we're just going to subtract off this 90 and subtract 90 from here. So angle B plus angle BCD equals 90. Now let's look at this other triangle, this triangle here. Similarly, we can say that the measure of angle DCA, measure angle DCA plus angle A plus 90. So this angle plus this angle plus this angle equals 180. And similarly, we can just cross these out and say, well, angle DCA plus angle A equals 90. Okay, sorry. We ignore that for a second. Ignore, go backwards, let's rewind. I'll see if I can delete this off the video. That's not what we want to show. The next thing we want to do is we just want to look at these angles here. Sorry. So angle BCD and angle DCA, we want to show that these two angles added together also equal 90. So the measure of angle BCD plus the measure of angle DCA equals 90. And how do you know that's true? Well, this angle plus this angle have to equal the right angle because they're adjacent angles. Adjacent angles added together equal the sum, equal the measure of the larger angle. Okay, so now knowing that that's true, well, if angle BCD equals, well, let's just rewrite this one. So if we can rewrite this line here, and we'll say the measure of angle BCD, and we're going to subtract a measure of angle B from both sides. So if we subtract the measure of angle B from both sides, we get 90 minus measure of angle B. Similarly, on the bottom, we're going to say the measure of angle BCD equals 90 minus the measure of angle DCA. Right, so because we just subtracted the measure of angle BCD from both sides. Right? Okay, so I know now if this is equal to, the measure of angle BCD is this, and the measure of angle BCD also equals this, then I know that if these are equal, then these two things are equal. So let's rewrite this using substitution. 90 minus measure of angle B equals 90 minus measure of angle DCA. Now let's subtract 90 from both sides to get negative measure of angle B equals negative measure of angle DCA. Divide both sides by -1, and you get the measure of angle B equals the measure of angle DCA. So then you can say that angle B is congruent to angle DCA. So the so angle B we've just showed is congruent to angle DCA. Okay, that's really important. And then another way to look at it is saying, well, if angle B plus angle BCD equals 90, and the measure of angle BCD plus the measure of angle DCA equals 90, then these two things have to be equal to each other. So let me just undo kind of all the work that we did here, because I want to write back. You can fast forward using YouTube if you want to get back and see all this work. But I'm going to get rid of it because I want to keep working on top of the same picture. So I want to sum up what we learned. Let's not forget what we learned. Let's mark that down. And let's just mark it down in yellow here. So we just showed that angle B is congruent to angle DCA. Okay. What can we say now? Well, if we know that these two angles are the same, we actually can also show that these two angles must be the same. Well, let's hold on a second and see why that must be true. Let's look at angle BCD. So angle BD, or triangle BDC. So in this triangle, we have an angle. Angle B is equal to, so this is angle, let's see. So let's say that this is equal to angle B plus, I have angle B and I have a right angle. And here I have in triangle BDA, or sorry, CDA. I have angle DCA, and I have a right angle. Wow, well, I have two angles that are the same. So by angle, these are similar triangles. So these triangles are similar. Okay, let's keep going. Well, let's look now at triangle BCA, the big triangle, and angle BDC. Okay, now we're going to look at this big triangle, right? Along with the little triangle. Well, the big triangle also has an angle B. It has a right angle in it, right? So the big triangle has BCA, so it's got this angle, and the little one has an angle B in it. So it turns out that these two triangles are also similar. So by angle, these two triangles are similar. Okay, and if two triangles are similar to each other, then the third one also must be similar. So it turns out that these triangles all must be similar. So this angle is extremely powerful. And so now we have these triangles that are similar. So we can say that triangle ABC, or triangle BDC is similar to triangle CDA, which is similar to triangle BCA. So that's part A. We've completed part A of our proof. Let's just leave that up there. And now let's build the relationships between the sides. Okay, so this is the next kind of big leap we're going to make. And I'm going to write it right here. We're going to do it right over here. And we're going to say, well, I'm going to write it out so and say triangle BDC is similar to triangle BCA. And it's important that you get the angles right? So the angles have to match up, going all the way back to less than 8 and 1. So angle B and BCA, we have to make sure that the angles that match are written in the same order. So B is the same as angle B. Then we have to go to our right angle. So in the small triangle, that's BDC. Now in the large triangle, it's B. Then we have to go to the right angle, CA. So now that we have these in the right order, we can match up our similarities. Okay? So I'm going to choose to do R times BC, R times side BC, the first and the last. Right? R times BC is equal to the first times the last, the length of BA. Right, so these are similar triangles, so I can take R and I can multiply it, in this case, by the hypotenuse. And that's got to equal the hypotenuse of the bigger similar triangle. Okay, and then I'm going to say R times BD, the short side. So R times the length of BD is equal to the length of the short side of the big triangle. Well, that's BC. Okay? So R times, so these are the similar relationships that must be true. Okay, so now watch what I do. So let's do the same thing for this other triangle. So we're going to now relate this triangle ADC is similar to triangle ACB. And remember, we're going to go A, the smaller angle, to D to the larger angle. And on the big triangle, we're going to go the smaller angle, A, that matches. Angle A matches angle A, but we got to go to the right angle, which is C, and then up to B. So these triangles are similar by this relationship. Here's our right angles, angle D and angle C, and angle A is the same as angle A. So now let's write R times the length of AC, first and our last. Well, that must equal the length of A times B. And then R times AD, length of AD must equal, well, AD matches to AC, must equal the length of AC. It's got to be true. Okay, so now this is part B. We have built relationships that we know must be true using similarity. Our knowledge of similarity says the relationships between the sides are a constant scale factor. Now we're going to move on to step C, where we're going to do some algebra to relate, to prove our Pythagorean theorem. This is very powerful stuff. You know, if you have to memorize it, you're going to have to watch this a few times. But each step, hopefully, is making sense to you, and you're seeing the power of similar triangles and how it can actually prove the Pythagorean theorem. So now let's use these sides. Let's just do some algebra here. And I'm going to say, well, if R times this is this, then I can take, I'm going to divide both sides by this length of BC. So we're going to do this one, and we're going to say, well, R is equal to the length of BA over the length of BC. And R is equal to the length of BC over the length of BD. Right? That's rearranging this one. And then I can set them equal to each other, because if R is equal to R, then this is equal to that. So BA, the length of BA over the length of BC has got to equal the length of BC over the length of BD, right? This has got to equal that because they both equal R. So we're going to take this and we're going to move this up here. The length of BA over the length of BC equals the length of BC over the length of BD. All right, let's do the same thing here. Do the same thing, rewrite these guys in the same way. Well, that's going to say basically R equals AB over AC, and R equals AC over AD. Let's write those up here too. And I'm going to do some swapping here in a second. Let's rewrite some of these letters, these links, because we know them. So we know that BA, this whole side here, that's our C, right? That's C. So let's just change that out for a C, because it's just going to be simpler for us. That's C. Well, BC is just A. So C over A equals, and BC, again, is just A. And now length of BD, we don't have a name for that. So we're just going to leave that as BD. And over here, we can do the same thing. A, B is, that's C, over, well, AC is B. AC is B. And AD, we don't have a name for that, so we're just going to do it like this. Now, we're going to cross multiply both of these. Again, we're doing algebra, so if C over A is equal to A over this, we can cross multiply and say, well, A times A is A squared equals C times BD. BD. And over here, we're going to cross multiply. And we're going to get B squared equals C times AD. Okay. Now, watch what we do. Watch what we do. We say, if this is equal to this and this is equal to this, I can add two things that are equal because this is equal to this. So I can just add this to my left side and I can add this to my right side because they're the same. These balance. If these two balance and these two balance, then I can just take this side and stick it on one side of the balance and this, and I can take it on the other side of the balance, and everything should still even out, right? This says, this is my additive property of equality. If these things are equal and this thing balances, I can just add these down. So let's just add these down. A squared plus B squared is A squared plus B squared. And this is equal to, well, I can't add these together because they aren't the same term. So I say C times BD plus C times AD. Now we are almost there. We are almost there. So now we're left with A squared plus B squared equals C times the length of BD plus C times the length of AD. Well, let's factor this out. Let's think all the way back to the end of 7th grade. And we can do this. We can reverse. We can reverse distribute, called factoring. Right? If we had C times X plus C times Y, that equals C times X plus Y. And we know that's true because we can distribute back and we get CX plus CY. Right? So we know that this is true. A lot of building blocks come into play in this proof. For those who have hung with me, great. You've done well. Now, what is BD? What is BD plus AD? What is this equal to? BD plus AD. If I add this side to this side, what do I get? Well, I get the whole side. And that's C. So let's write that down. Let's just replace this with C. I get A squared plus B squared equals C times C. Well, what is C times C? Oh my goodness. A squared plus B squared equals C squared. And we have a happy, spinning happy cat because we have proved the Pythagorean theorem using our knowledge of similar triangles and algebra. This is so cool. This is why math just rocks. And why all the work we've been putting in makes this cat just go meow, meow, meow. This was awesome. Awesome, awesome. Now, you've done some great work here. For those of you who followed, you can rewind this and learn the exact steps. Maybe you can memorize it, maybe if you have to. But if you hung with me and understood most of this, kudos to you. And now, let's just go and let's serve up something that's far easier. Let's just look at how we might utilize this information, Pythagorean theorem, to solve a problem. Now I'm going to just label a few pieces, and then you're going to fill in the blank, and then you're going to know how to do all the homework. Okay, so let's say that this side here is 13 This side is 12. This side is 15. We'll just label these. A, I don't know that you need to label these. A, D, C, and B. Now let's just use the Pythagorean theorem, and this is also a right angle. Let's just use the Pythagorean theorem to find the length of DC, the length of CB, and then hence the length of DB. Right, so we want to find this, and then I want you to find that. That's our homework help. This is our homework help. We'll put it in script, or also known as cursive. Now I want you to sit back, solve this, knowing that a squared plus b squared equals c squared in a right triangle. Okay, so let's find, so now pause and try. Pause and try. All right, I assume you're back. Assume you've had your little break, and now let's figure this out. So let's look first just at this triangle here. We're just going to look at the triangle on this side. And so what's our A, our B, and our C? Our A is one of our legs. B is our other leg, and C is the side opposite the right angle. So let's write our truism here, our numbers. And so our C is 13, our B is 12, and our A we don't know. Okay, so our A, we don't know our A. Our B is 12, so 12 squared, and our C is 13 squared. So we get A squared plus 144 equals 169. Subtract 144, and we get A squared equals 25, so our A equals 5. So DC is equal to 5. Hopefully now, let's see if you can figure that out for this guy. This triangle here. We're going to do the same thing here. And now we can call this, hopefully you pause. If you only did one part, now pause and try this one. And I assume you're back. So we'll call this A, B, and C is 15 because it's opposite right angle. You can't just make any of them be A, B, and C. C always has to be the one opposite the right angle, or this doesn't work. We get A squared plus 12 squared equals 15 squared. Okay? A squared plus 144 equals 225. Minus 144 minus 144. And we get 81 equals A squared, or A equals 9. So CB equals 9. So if DC equals 5 and CB equals 9, then DB equals, just them added together, it equals DC plus CB, which is equal to 5 plus 9, which is equal to 14. Let's lay down our happy cats. And let's call that a day. So, that was a lot of work. We had a proof. It was very involved. But again, each step, you should be able to understand each step. If you focus on one thing at a time, all the building blocks should make sense. And if it doesn't, go back and listen and make sure you get it. Because when you conceptually understand this stuff, you really wield the power. So we are getting more powerful and our brains are getting more strong, and we are gaining the self-efficacy. Those of you who will know math in the future, those are the ones who will wield the power. You will get the better jobs, and you have the skills that employers are looking for, so you will get a job someday. Until next time, happy math, happy cat, happy days.